Welcome to another Hyperstition broadcast. Today's topic is very interesting. It's very weird. It's very spooky. It is the nature of reality. It's a theme we'll return to again and again. More specifically, it is the interpretations of quantum mechanics. And Einstein was such a genius. He didn't just finish general relativity. He immediately started pointing out all the weirdness of quantum mechanics, and specifically this Einstein-Podolsky-Rosen paradox, which is really, it seems like in quantum mechanics, things may happen instantaneously. And this is the measurement of entangled states. And, this is kind of weird. Is light going faster than, or is the information going faster than the speed of light? Or alternatively, are things not really determined until you look at them? And this breaks our conceptions of what we think of as causality, things being well ordered in time and not breaking the speed of light, which is the speed of causality, or things being real independent of observation, or local realism or locality. This concept of local realism was later explored by John Bell and Bell's inequality, which kind of set mathematical limits on, assuming quantum mechanics is an accurate description of reality, what can we actually go measure? So this is a complicated topic and something that I've just revisited again and again and again. It's hard to get stick in your head. It's hard to develop intuition for this. So I'm going to invite today a good friend, or a new friend, Richard Behill, who is one of the best science explainers I've ever come across. And it's you're listening to this because I explain science stuff, and he is better than me at getting into sophisticated physics and explaining it in a way that is comprehensible and approachable. And so I will invite Richard up here. Hey, Richard, how you doing?
Hey, thanks for the nice introduction. I appreciate the kind words, and looking forward to talking about quantum physics.
Absolutely. I mean, and before we get into that, I mean, you had an interesting background. So you also worked in superconductivity in microelectromechanical systems, MEM systems in Santa Barbara for a while. Kind of, professional engineer for a long time, and recently you've now pivoted into explaining difficult physics concepts to a pretty big audience on YouTube.
Yeah, now I'm a YouTuber. Yeah, so I worked 7 years in R&D on microelectromechanical systems and superconductivity. Lately, my channel has been growing. It's something I started as just like a side project, but it's really been taking off, and it's something I really enjoy. So I've been very fortunate that over the past few months, I've been able to transition to doing that full time. And it's been a lot of fun.
Yeah, and I think, I've seen your video, your channel stuff. It's really good. It's really sophisticated, nuanced investigations of these things. I think this topic in particular, like Einstein-Podolsky-Rosen paradox and Bell's theorem, and this concept of entanglement, is one of these things that is, I think, often treated at a superficial level. It's sort of like, oh, quantum mechanics is spooky, and that's kind of the end of the story. That's the kind of thing you'd read in like a popular science magazine or whatever. But I think, as there's a lot more to it, and there's a lot more nuance, and there's a lot more like interesting places to take it. So I'm excited to hear what you have to share with us today. And I think you're going to give a presentation kind of starting at the beginning, really. Like, what is the framing of this supposed paradox, and how do we approach it, I guess, experimentally and mathematically?
Mm-hmm. Yeah, sure. So to your point, quantum entanglement, spooky action at a distance, the EPR paradox, these are all super interesting topics. And I think pretty much everyone's heard about them, even people who aren't really interested in physics. But it's one of those things where so often when these ideas are presented, it's at a very surface level. And so people come away with it thinking, okay, well, so quantum mechanics is spooky, but why? What exactly does that mean?
Yeah.
And then that can go one of two ways. Either they think it's spookier than it is, and they mystify it into like, telepathy is real and we can astral project, and it goes in like a woo-woo direction. The other direction it can go is people say, well, I'm sure if you look at the technical details, it's really not actually spooky. And probably what's happening is people are making making too big a deal out of something that's not actually that spooky. The truth is, it's somewhere in between, or maybe it's I don't know if in between is the right word, but the reality is, quantum entanglement, the EPR paradox, and which isn't really a paradox, but Bell's theorem, which is like the follow-up to that, it is genuinely spooky. Now, what I'm about to say is going to sound a little bit crazy, but after having learned about Bell's theorem, it left me deeply existentially unsettled. To say that Bell's theorem, these Bell correlations are weird, is a dramatic understatement. Bell's theorem, I recently did a video called Bell's Theorem, a glitch in reality, and it genuinely is a glitch in reality. I mean, when you see, when you really walk through Bell's paper and contend with his argument, and you look at the experimental data, which backs up what he's saying, there's just no making sense of it in the context of conventional sanity. Okay, so that's a strong statement, but in order to make sense of the physics, both theoretically and experimentally, you have to give up something about the way you think about reality. And no one knows exactly what you have to give up, but it's like one of a few things, and whichever one of those things it is, no matter what, you're thinking like, whoa, what even is reality then? So so the way I like to think about it, and by the way, no one knows, there's no good answer to what's going on with the Bell correlations. What we do know is that there is no explanation for these correlations in the context of a model of physics that has that is locally real, that exists within the context of local realism. There's a subtle assumption there about measurement independence, but we don't have to go into that at the moment. But in any case, sorry, I feel like maybe I'm rambling a bit. But
no, this is good. This is good. We're going to get into it. We're going to get into it. Yeah.
Awesome.
And I before we get into that, I think this has now spawned a kind of interesting field of like theoretical metaphysics almost, where it is like interpretations of quantum mechanics and trying to implement these into like measurable, I guess, like taking thought experiments and then putting them into an experimental setup and trying to measure kind of what view is correct. And I know there's this concept of local, this is from extended Wigner's friend thought experiment, local friendliness, which is, I had another friend write a paper on this. I'll try to get him to present these days. He's busy being a venture capitalist, investing into quantum, quantum tech generally speaking. But well, here, let's start with the EPR paradox. And I think this is a better layout for us. Here we go. And I'll put these up here too, so people know where to find you, where to follow you, all this kind of stuff. And I mean, I'm here for it. So let's dig in. And I would say don't shy away from the math, and I'll do my best to help translate that. But let's give it a proper technical treatment. Let's not shy away from this. The floor is yours. I'm stoked to be here.
Oh, thanks. Yeah, sounds good. Well, so I guess just for those who haven't seen my videos, just a quick overview. So if you want to understand quantum entanglement, as far as like spooky action at a distance and Bell's theorem and all that, there are two papers I would recommend. I mean, there's many papers, but there's like two main ones. The first one is a 1935 paper by Einstein, Podolsky, and Rosen, and it's called "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" So this is also known as the EPR paradox paper. In this paper, in 1935, quantum mechanics was still very new, and of course, quantum mechanics is very strange. So back when it was new and strange, you had people like Einstein, Podolsky, Rosen, many people were thinking, okay, well, is this a complete theory or are we missing something? So in quantum mechanics, you have things like, there's position, momentum, energy, but is there some kind of additional hidden variables that the model doesn't yet include that would have to be supplemented or added on to the theory in order to get a complete theory? And the argument put forward by Einstein, Podolsky, and Rosen in this paper is that quantum mechanics is incomplete because if you assume quantum mechanics is complete, then there's an apparent paradox. So the thing about the EPR paper, this was written in 1935, and when you read it today in the year 2026, it reads like a bit of a historical document. You have to read it with the perspective that this was at the dawn of quantum mechanics pretty much, and people really didn't know what we know today. But it was sort of like, Einstein and friends were like raising like a red flag and saying, hey, something seems to be wrong here about quantum mechanics. but they didn't really appreciate exactly what was wrong about it. They did, however, put forward a very interesting argument as to why quantum mechanics appears to be strange or unusual or paradoxical. And so this paper, 1935 EPR paper, is definitely the first thing that you want to look into if you're interested in understanding spooky action at a distance, as it's called, or quantum entanglement. Also, on my YouTube channel, I have a video called the EPR paradox, and it goes into this paper, line for line, equation for equation, going through the whole thing and talking about, you know, what every part of it means, and also including contextual information and animations that go into the technical details of the math. Then the second paper you want to read after the EPR paper, you want to read Bell's paper. This was written in 1964, and it's called.
This is.
Oh, yeah, there it is.
Sorry, this was Einstein's paper. I should have this up, but yes, this is Bell's paper.
Oh no, that one is the Einstein's paper there.
Oh.
Yeah, Bell's paper. That's the yeah. I know it's confusing because so Bell's paper is called on the Einstein-Podolsky-Rosen paradox because it's like a sequel or like a rejoinder to the EPR paper, and this is Bell basically what he's saying is okay. Einstein, Podolsky, and Rosen put forward this argument about quantum mechanics being incomplete, apparently paradoxical, and now Bell comes in 1964 and says, sorry, Einstein, I know you want to add additional variables to make quantum mechanics complete, but even if you do that, quantum mechanics is still weird. There's still these apparently non-local correlations, which to this day, no one really knows what to make of, but you can kind of imagine it as non-local wave function collapse. And then don't think too hard about relativity. But anyway, so
this is Einstein's quote. He's like, you know, God doesn't play dice with the universe. He believed in I guess what you call like hidden variables or a super deterministic theory where things are not. Is that correct?
Well, so there's two different things there. There's hidden variables. Actually, there's three things. There's God doesn't play dice with the universe, then there's hidden variables, and then there's superdeterminism. And there's some connection between all these things. But Einstein was unsatisfied with the role of probability in quantum mechanics because he had this very classical, very understandable sentiment that the world shouldn't just be random. Like where would that randomness even come from? So he's saying God doesn't play dice with the universe. And of course, Einstein wasn't religious in the sense of, you know, when he says God, he's not talking about a guy in the sky. He's saying that in the sense of Spinoza's God. And so basically he's rejecting the concept that there should be probabilities at the bottom of physics. To your point about hidden variables, and I don't want to speak for Einstein. I don't know what his point of view was on that, but just based on reading the EPR paper, at least one of the things that Einstein had to say about hidden variables is that we seem to need them in order to restore local realism to quantum mechanics. He turned out to be wrong about that. But then there's another layer of nuance because there could be hidden variables that quantum mechanics doesn't yet take into account. It's just that if there were, that actually doesn't resolve the paradox that was pointed out in the EPR paper. And then superdeterminism, that's a whole nother, I mean, we could talk about that for hours.
Okay, that's okay. We'll leave that aside for now. Yeah. Okay, well, okay, I think this is pretty good framing. Why don't we get into, I guess, the nature of why is this a paradox in the first place? I think you said it well. I mean, I have this mindset, like there's no true paradoxes in reality. Like it's more of a paradox probably because it just defies how we think things should work or how we experience them in our lives. Like we don't experience things popping into existence or you know, like I turn around, the table is still here type of stuff. So let's get into why I think what is the nature of this paradox or why do they frame it as such?
Yeah, sure. Yeah, where to begin? Okay, so the slide you're showing here, I think this is a good thing to meditate on for a moment, just because, so these PowerPoints, these are like screenshots from my videos on these papers. And those videos are like over 5 hours total, which is, it sounds long, but that is the right amount of time if you want to go into like every detail. For today, of course, we want to do more of a summary. But the EPR paradox, what is shown on the screen there, psi is a function of x1 and x2. That is an entangled two-particle state. And I probably should have Probably should
And
have.
psi usually conventionally represents the Schrodinger wave equation, which describes how something will evolve in time. It is a wave equation, right? It has like a second order spatial component, a first order time component. It relates I think conventionally the position of a particle is a function of its potential or something like that, right?
Yeah, exactly. So the Schrodinger equation, yeah, it's second order in space, first order in time, which seems like that should be a diffusion equation, where if you have a wave function and then you look at its, it should go like that. But psi is a complex valued wave function, and so actually it's able to swing around in the imaginary, in the complex plane. And so that's why, if you look at that the colorful blob on the screen, you can see you have a complex valued wave packet, and then the little rainbow thing on top is sort of another way of looking at it in terms of amplitude and phase. But yeah, so you're right. And just to explain, physically why we have wave functions in quantum mechanics, in the everyday world, the macroscopic world that we live in, we have there is such a thing as like a solid object. Like this is a cube of pure tungsten. It's very solid, and it's like I can think of it as like it's a thing. It exists. It has some position and it has some velocity. Everything's very sharp, very well defined. But when you zoom in at the subatomic level and you look at these elementary particles, electrons, and all that sort of thing, the concept of like things like position and momentum, they're not what we would expect them to be. It's very strange. And so if you then say, well, okay, how do you describe a particle in a context where things like position and momentum don't have their classical meaning? Well, you resort to the mathematical machinery of quantum mechanics, and where the state of the particle is encoded in a wave function. So that's the wave function, and the Schrodinger equation gives you the time evolution of a wave function in the non-relativistic limit. And by doing various mathematical operations on the wave function, you can calculate things like the expected position, the expected momentum of the particle, as well as the variance on those expectations. And as it turns out, because position and momentum are related in a certain kind of way in quantum mechanics, if you try to localize a wave function, say in position space, so you have a wave packet, and you try to squeeze it to one specific point, well, what happens is it's too scrunched. The Laplacian of the wave function becomes way too high. And so as you try to localize it, you can imagine it getting all jittery, and like now its momentum is all undefined. Mathematically, the Fourier transform of a delta function in position space is a plane wave in momentum space. And so if you try to say, I want this particle to be exactly right there, well, now you know nothing about its momentum. And vice versa. If you try to say, I'd like to make a particle whose momentum is a very precise value, a delta function in momentum space, well, that's going to have to be a plane wave in actual space. And so then you're not going to know its position, because a plane wave is spread out uniformly across space. And so, but then you can also go somewhere in between, where like what I show there, you have like a wave packet with some distribution of momentum and some distribution of position. And these observables are kind of, they're not sharp like in the classical world. They're sort of these fuzzy statistical things.
Right. And these could represent perhaps like 2 electrons, for example.
Yeah. Okay. So that brings us to the topic of a 2-particle wave function, and that's where all the weirdness comes in.
Right.
So,
well, I mean, already it's kind of weird. It's like already particles aren't actually like single point things. It's fun, or it's nice to treat them like that, but actually they have a distribution in space. And I mean, now we see this. It's kind of like the Bohr model of the atom was like not accurate, but very useful. And you can still use it for like organic chemistry, but they're not actually like point electrons. They are spread over in space. So reality is already weird, but it's about to get weirder. So what happens when you have now 2 particles?
I have my hydrogen mug. You can see you have the ground state, 2-0-0 state. And yeah, it's electrons get fuzzy in quantum mechanics.
Yeah.
And you're right, even without a 2-particle wave function, quantum mechanics is already weird. I mean, a particle and position and momentum, uncertainty principle, there's plenty of weirdness throughout quantum mechanics. But where it gets really weird is when you have 2 particles in a wave function where the particles are entangled. Mathematically, what it means for a wave function to be entangled is that you can't cleanly separate out the wave function as a product of the two individual wave functions. So what that means intuitively is if you have, let's say classically, if you have one electron here and another electron there, with common sense, you can think, okay, this is one electron and this is another electron. And if each one is a little cloudy wave function and you're not sure exactly where it is, you can still say, well, it's somewhere here and this electron is somewhere there. And you can talk about it in terms of two distinct electrons, even though the electrons are all identical. You know, these are excitations in the electron field. Every electron, it's the same mass, same charge. There's nothing different about them. But you can still have a state where it's separable in the sense that you can talk in terms of this electron and that electron. However, in quantum mechanics, it's possible to prepare an entangled state where even if you have these electrons separated in space, you can no longer talk only in terms of this electron and that electron, because the wave function depends on more than just the product of these two wave functions. There's a mathematical connection there where it's no longer meaningful to talk purely in terms of one electron or another. Their quantum state is entangled.
And so like a classical analogy comes to mind. Suppose you have like two billiard balls on a pool table and they hit each other and they bounce off. And I know momentum is conserved. So if I see the direction and speed of one ball, I could infer the direction and speed of the other, because the initial net momentum must have been a certain number or value. And then at like time 2, you know, I expect that the total momentum is still the same. But is that, are you saying there's something beyond just this like observation of conservation of momentum, or conservation of some state or quantity that describes the system?
Yeah. Well, so in the specific example shown on the screen there, we have psi of x1 and x2, and it's written in two different forms. First, it's written as an integral over momentum space. That's that purple integral over dp. And then second, it's written as an integral over position space, where we have the product of two Dirac delta functions. And what that corresponds to physically, it's a bit hard to imagine, but it kind of ties into your billiards ball example with momentum. In the first equation, if you sort of interpret that in the context of quantum mechanics, what you have are two particles whose momenta are perfectly anti-correlated. So this is the model put forward in the EPR paper as an example of an entangled state. And in this state, we imagine two particles moving just along a single axis, the x-axis. And what is encoded in this wave function, this two-particle psi, is that whatever the momenta of the particles are, they're going to be equal and opposite for sure. So if you measure one particle has momentum p, the other one has momentum negative p. What's not defined in this wave function is exactly what that momentum is. And so that's where it breaks from the classical idea of having, you know, a collision and then there's momentum and it's conservation of momentum. Here we have a correlation which can persist even if the particles are spatially separated and even if the momentum is not precisely defined. So you can have these two particles existing with a distribution of possible momenta and a guarantee that if you measure their momenta, they're going to be anti-correlated. But the actual momentum itself isn't exactly known or isn't even exactly real until it's measured. What's interesting about this is if you then think about this in terms of the positions of these particles for this particular state, you find that the positions are going to be perfectly correlated with an offset of x naught, which appears there in the second equation. And so this two-particle wave function is the example used in the EPR paper. And it's a bit contrived. Physically, it's not the most realistic wave function in the sense that it's very sharp. You have a perfect anti-correlation in momentum, perfect correlation in position. In reality, if you wanted to create such a state, not sure exactly how you would do it, but maybe you could do a spontaneous parametric down conversion where a photon comes in and two photons come out, and you can probably design an experiment to create a state that's something like
that. That would be like in a nonlinear optical crystal or something like that? Like
Yeah,
right. I've heard this more in the spontaneous up conversion, which is cool, where it's like we're going to take, you know, larger wavelength photons, mix them together in some crystal and get a shorter wavelength photon out. Just like otherwise very hard to do. Short wavelength photons are very expensive to produce. Right.
Well, that's why oftentimes if you look at these like high-powered UV lasers, they often will start off with IR lasers and then double or triple up the frequency.
I'll brief aside just because this is supposed to be casual, but I once visited a lab. I was thinking of going into plasma laser wake field acceleration tech, which is like the next generation of accelerator technology. And so I visited this lab, and they had like the world's most powerful, like ultra fast laser or something. They had a nonlinear optical element that was like the size of a pancake, because they dumped so much beam power into it. It had to be that big, or else it would melt. It was like so cool. And yeah, it was doing this photon up conversion thing. Okay, but so let's continue with this. I think this is a good illustrative to example. Sure, maybe it's not like the most physically accurate thing, but it's enough to illustrate, I guess, what Einstein thought was so weird.
Exactly. Yeah. So it's not the most physically realistic wave function, but it's great for interrogating the mathematical structure of quantum mechanics. So it was chosen for mathematical convenience and to make a philosophical argument. The fact that it's not the most physically realistic wave function is okay, because in reality, you could make one that's very similar, but with some Gaussian envelopes corresponding to the experimental messiness. But that doesn't change the fundamental structure of the argument put forward in the EPR paper. Now, later on in Bell's paper, he is considering a similar system in that it's two entangled particles. But in that case, you have a spin singlet state. So you have particles whose spins are entangled. And that picture is more experimentally realizable, and it's more, you can think about it as far as it being more realistic. But in any case, the details of the entangled state are not super important. What does matter is the way in which you can have two particles that remain entangled despite being separated in space. I mean, that's really the problem right there. That seems to go against the concept of relativity, because how can it be, when the wave function collapses, how can it be that you have instantaneous wave function collapse? Anyway, sorry, I might be getting a bit too far ahead there.
Absolutely. Let's keep. I mean, should we continue through these kind of visual aids to kind of anchor us?
Yeah. Do you mind? I think I can move to the next slide here. Actually, there's a ton of slides here, but I'll just.
You try clicking. Can you?
Yeah, we'll do. Yeah, so these are just screenshots from my videos. There's no way of going through all these slides today, but I think this is a good one to look at. Yeah, so this is like a flowchart of the argument put forward in the EPR paper. And basically, sorry, okay. Sorry, on my end, I see there's like this overlay that's, there it goes. Okay, all good. So the argument is basically, if you look at the top left of the flowchart, quantum mechanics is either complete or incomplete. So, and then those little symbols there, one and not one, in the paper, the EPR paper, the statement number one is, we're going to suppose that quantum mechanics is incomplete. And that's something that they want to demonstrate in the paper. So if it's incomplete, or sorry, if quantum mechanics is complete, that's the negation of their statement that it's incomplete. And so then if you go in that branch of the flowchart and you say, okay, suppose quantum mechanics is complete, doesn't need any additional hidden variables, then they show that that leads to an apparent paradox. And then they sort of recoil in horror from that paradox and say, you see, therefore quantum mechanics must be incomplete.
Yeah, kind of argument by contradiction or something, or reductio ad absurdum or something.
Exactly. Yeah, it's yeah. And so
what is this? So let's suppose it's complete. And the first part is this uncertainty principle, and that leads us to this claim that non-commuting observables can't be simultaneously real. And what does this mean for two? And observables mean things you can measure, right? So they are like things you could actually measure. So they're real valued, I guess, in the mathematical sense. You don't tend to measure imaginary values. That's like a bookkeeping convention for keeping track of phase of something. What is this non-commuting? What does that mean, I guess?
Yeah, so the classic example is position and momentum. So basically, if you have a wave function, the position and momentum are non-commuting quantities in that, well, actually, let me just check if I have a slide on this here. Oh yeah, okay, I don't know if this is too much detail to go into, but basically—
No, it's fine.
Cool, all right, so yeah, in quantum mechanics, you have these things called the position operator and the momentum operator. And if you have and so you use these to calculate like what's the expectation value of position and momentum. So the momentum operator is a good example. It's negative I h bar times the derivative. So the idea is that if you have, sorry, I'm just reading through this slide real quick. I haven't really looked at this in a little while, but if you apply the momentum operator to a wave function, you're basically taking its derivative and then multiplying that by a purely imaginary scale factor, negative I h bar. The reason that's the momentum operator is because then the momentum of a particle, if you know its momentum, if you have it in what's called a momentum eigenstate, then the momentum value is going to be the eigenvalue of that momentum eigenstate. And so when you think about what is the kind of mathematical equation where when you take its derivative and apply a purely imaginary scale factor to it, it gives you, that is the same operation on that function as scaling it by a real valued eigenvalue. You find the plane waves, e to the I, p x over h bar or something. Sorry if I'm making a technical mistake.
I mean, just the operator to get the momentum from an equation that describes its position, it seems intuitively like reasonable that we would take the derivative with respect to space, because it's like classical momentum is like velocity, right? Which is like the derivative of spatial position with respect to time. Oh no, actually, sorry, I just confused myself.
Well, yeah. Sorry, go ahead.
Yeah. So okay. So what were you saying here about this momentum operator? We expect the momentum to be the eigenvalue of some. What was this again?
Yeah. So in general, an observable quantity in quantum mechanics, the wave function encodes the state of the particle, and so if you want to measure some observable quantity of a particle, those are going to be eigenvalues of the operator associated with that quantity. And then when you measure that value, the wave function is going to be put into an eigenstate of the operator of the observable that you're measuring. So for example, if you were to measure the position of a particle, and let's say you were really, for the sake of argument, you really want to measure and say it's exactly right here, well, then you're going to have to put the wave function into a Dirac delta function distribution, as far as like, you got to localize it at that point. Or if you wanted to really, on the other extreme, if you wanted to really measure the momentum of the particle and get a specific momentum value, well, you're going to end up putting the particle into a plane wave solution where across the whole wave, that momentum operator, the derivative, gives you the same result everywhere you look. And then in reality, because reality is messy, you always have kind of something in between. But yeah, I wonder, is this slide, is it too, maybe we can kind of zoom out from this a little bit.
I think it's making sense. Basically, it's normally, my understanding of this commutator thing, it's the order of operations matters, right? That's really what it's getting at. It's that it's like, a normal, if you're just multiplying like real numbers together, like a times b is the same as b times a. And so they would, if you take the difference between these things, it's zero. But you're saying in this case, there's not a zero difference in terms of the order of operations, whether you were to measure position first or momentum first. Is that an accurate framing?
Well, the thing that, so you're right about the commutator being related to the order of operations mattering. The thing that I'm getting at in this slide, and it is kind of a technical point, but there's a result in quantum mechanics that if you have operators corresponding to two observables, and the operators don't commute, in the sense that if you first apply one operator to a wave function, then apply the other operator to that, that's going to be different than having applied the other operator first and then the original operator to the wave function. And so, and what this slide shows is if you apply the position and momentum operator to psi and compare that to applying the momentum and position operator to psi, you end up with two different results. And the difference, depending on which way you do it, is going to be I h bar times psi. And so that's what's meant when we say that the commutator of the position and momentum operators is I h bar, which is non-zero. And then from that, in quantum mechanics, if the commutator of two operators is non-zero, then there's going to be an uncertainty principle where at most, so in this case, if delta x is your uncertainty in position and delta p is your uncertainty in momentum, then that has to be bigger than a finite number, in this case, h bar over 2. And anyway, so that just relates the non-commuting nature of position and momentum to the fact that there is an uncertainty principle regarding position and momentum. And that gets back to kind of zooming out to what we were talking about these quantities being not simultaneously real. is that if quantum mechanics is complete and we take it at face value and say, okay, the math is right and all this operator stuff is true, then there's no way to take a particle and for it to have a real precise position and momentum at the same time. It can't be done. So that's what's meant by two non-commuting observables not being able to be simultaneously real.
Yes, and in this, the formulation of this uncertainty principle, it's like the variance, or is it the standard deviation or the variance of these things is greater than or equal to 1/2 times the expectation value of this commutator relationship? It's like that. That's what these brackets, or is that that's the expectation value, right?
I always get standard deviation and variance confused. That's something I'm always mixing
They're just
up.
like one is a square root of the other, I think. Standard deviation, square root of variance.
Yeah, and I believe in this case it's variance, but don't quote me on that. I always
Sure.
those things
but this is to say essentially, like statistically speaking, if you were to like average over many measurements on the order of operations here, you would find that there's some like lower bound on the uncertainty of these two things with respect to each other. That's what we're getting at.
Well, this one's not so much about averaging over many observations. It's more like this gives you a limit to where if you want to localize your particle and make it really like it's right there, then this sets the limit on what your momentum uncertainty has to be. So like if we look at like a macroscopic object and say if I hold it really still, I can say its position is right here and its momentum is there's no momentum in my reference frame. But if h bar were a super big number, like a macroscopic number, then if I hold this still, you can kind of imagine it like probabilistically freaking out as far as its momentum. It's like, oh, is it, or no, wait, I think I said that wrong. But if I'm holding it here, then its momentum is weird. Or if I want to say, okay, it's going at a certain momentum, then it gets a little fuzzy in space. So that's if h bar were a big number, but h bar is a very small number, and so usually we don't have to worry about that.
You made me think of this hilarious thing just now, like h bar being super big is like Minecraft universe or something. It's like the minimum smallest size of something is like super big. But not quite, because Minecraft is not a quantum mechanical environment.
Well, yeah, but that's kind of it's an interesting comparison. Yeah.
Okay, I think this makes sense so far.
Let me give me one second. I just have to blow my nose real quick. Give me like 1 second.
All right, interesting.
There we go. Now I won't be sniffling as much. All right, where were we? So let's go ahead and maybe zoom out back to here.
Yeah. Okay, so this is the first thing. If it's complete, then two things that we expect to be normally, conventionally, we could like think of these things both being independently measurable, can't both exist at the same time in some real sense. This is the non-commuting observables can't simultaneously be real. Right.
And that's like standard, that's the standard orthodoxy in quantum mechanics is if you have non-commuting observables, they're not simultaneously real. Though people can say, what do you mean by real? Is it like epistemic or ontological? But the point is, within the context of quantum mechanics, it doesn't make sense to say, let's measure the position and momentum at the same time to arbitrary precision. It just can't be done. And for really mathematical reasons, like from a Fourier analysis perspective, if you try to localize in the time domain and the frequency domain at the same time, it doesn't, there's no way to do that because the Fourier transform of a Dirac delta function is a plane wave and vice versa. So yeah, that's that thing about them not being simultaneously real. But then this thing about quantum entanglement, that part with the yellow arrow that says psi thought experiment in part 2 of the paper, they make an argument based on this entangled state that it appears that you can have non-commuting observables that are simultaneously real. Critically, this assumes local causality, which is that cause and effect can't go faster than the speed of light. And then when they establish that, and that's the interesting thing is what that yellow arrow represents, the entangled particle thought experiment. But having established with that argument that non-commuting observables can, at least in some contexts, appear to be simultaneously real, then that's the paradox where they say, okay, well, what is quantum mechanics saying then? Can position and momentum be real at the same time, or can it not? And so then that's the paradox they back away from and say, okay, the assumption that quantum mechanics is incomplete, that's what must be wrong. So therefore, quantum mechanics is incomplete. So therefore, we need additional variables. but their meta logic here is a little bit wrong. Their math is correct, but the way they interpret it is wrong. Because the reality is, the assumption of local causality is not valid. At least for when you're dealing with entangled, quantum states.
That's how they get to this contradiction, because they've assumed some premise that you can't have superluminal information transmission or something.
Exactly. Now, depending on what you mean by information, but yeah. So the thing is, if you take out the assumption of local causality and you allow for something like instantaneous wave function collapse, then it doesn't follow from their investigation of their two-particle entangled state that the non-commuting observables are simultaneously real. Because in that case, what it would be instead is that just the wave function can be collapsed in different ways, but you never have to have two non-commuting observables that are real at the same time. It just comes down to which thing you want to measure. But maybe we can dive into what exactly their argument was with regards to psi.
Yep, that sounds like the key point here.
Cool, sounds good. Trying to think of how the best way to do that is. Let's see.
Do we further through in your presentation slides? Is this something you covered? Yeah,
sorry. I'm flipping through the paper real quick, trying to think of where we should start off as far as the entangled state argument. I mean, I think it all comes down to equations 7 and 8. So yeah, let me skip forward to those.
Okay.
I have a lot of slides. By the way, if anyone's interested in the real details, I recommend, well, first reading the paper, but I do have a video that goes into all these details. Let's see, is this the right slide? Yeah, I guess, oh, whoops, I went too far. I guess we can start off here. So the idea with the two-particle wave function in the EPR paper is, imagine you have two particles, call them 1 and 2, and at first they're interacting. So the wave functions are getting all entangled, and so you have an entangled state of particles 1 and 2. So in this diagram, imagine we have one spatial dimension, the x-axis, and then imagine time, as you go down in the diagram, that's forward in time. So then what this diagram is trying to represent is you have this entangled state with particles 1 and 2, and you send the particles their separate ways in space. But what these yellow horizontal lines, what I'm trying to indicate with that is that even though these particles are separated, the wave function is not separable. It's still an entangled state. And the specific state is shown there in that equation. That's that state we were talking about earlier with anti-correlated momentum and correlated positions. And so then the idea is you separate these particles. Now you have 1 is over here and 2 is over there. And the argument is, by mathematically analyzing this wave function, they show that if you measure the momentum of particle 1, then particle 2 is put into a momentum eigenstate for this particular state. But they also show if instead you measure the position of particle 1, then particle 2 is put into a position eigenstate. And that's the problem, because particles 1 and 2, assume they're separated so far out, and you think about this so quickly that there's not even light can get between one or the other. These things happen in different light cones. So if you're able to affect the wave function of particle 2 just based on what you choose to measure at particle 1, either position or momentum, and if in fact it's true, as according to quantum mechanics, that then particle 2 would be in either a position eigenstate or a momentum eigenstate, and you assume local causality, so you don't have instantaneous wave function collapse, then you'd have to assume, okay, well, particle 2 had a specific, precisely existing position and momentum, because otherwise, how could particle 2 know what position or what momentum to be? Because the thing is, at particle 1, if you have a wave function whose position and momentum neither are precisely known, it's a fuzzy thing. Well, you can say, okay, if I measure the position, maybe I'm squeezing it into a delta position eigenstate. If I measure the momentum, maybe I'm massaging it into a momentum eigenstate. And that's fine. So that's why it's not a huge deal that position and momentum can't both be precisely known at the same time. But what's super weird is there's no massaging that can go from particle 1 to particle 2 if you assume local realism. And so then you really do run into a problem of how can it be that we could have a position eigenstate or momentum eigenstate at particle 2, just based on what we choose to measure at particle 1. That seems impossible.
Mm-hmm. But this is still not breaking this commutation relationship for individual particles. Like this individual particle still, you would only measure its position or momentum? Or are you saying,
Yeah.
I get this thing, it's like they're entangled, and so measuring one thing over here can somehow determine what the properties must be over here, even if they operate in different light cones. But is that also breaking this thing where it's like I can't have position and momentum for a single particle?
That's a fantastic observation, because that is so smart. That's exactly the right question to ask. Because
I don't know. A second ago, I just said, "Oh yeah, the momentum. Yeah, momentum is the time derivative of space for classical objects." So, I mean, clearly, I'm not.
No,
but all right, go ahead.
Yeah. Things like, I mean, I say stuff like that all the time. It's hard to speak on the spot and do math at the same time. I mean, it's just like,
that's why we're here, man. This is
yeah. But to your point, that is a great point, because so let's say we only have one pair of particles, so we're not averaging over many measurements, just one. Then so there's one pair, so you have one particle at particle 1 and one particle is particle 2 over there. If you measure the position of particle 1, then particle 2 gets put into a position eigenstate. If you had measured the momentum of particle 1, then particle 2 gets put into a momentum eigenstate. But you can always say, well, but it wasn't both of those. It was only one or the other. And so in that sense, is it really the case that the position and momentum of the particle are simultaneously real? Or, so you can kind of, it depends on what you mean by real, like what even is reality? But there is genuinely something weird about this thought experiment, which is that even if these things, if you want to be really strict about what counts as being real, just the fact that you can choose whether particle 2 is going to be in a position eigenstate or a momentum eigenstate based on a measurement decision at particle 1, that on its own is already very strange. And so that's like, the way to get out of the EPR paradox is to just say, okay, it's strange, but for whatever reason, we do have non-local wave function collapse. Or something mathematically isomorphic to it. There's ways of sweeping the non-locality under the rug in your definitions of your quantum mechanics. There's also many world superdeterminism, but no matter how you look at it, it's very strange.
What it also, like this, it's open. I don't know if it's open debate or if there's strong arguments as to why, even if you have this instantaneous wave function collapse, why that could not perhaps actually transmit useful information in some way. I know I've looked into this a whole bunch, and it's sort of, I saw yesterday Sabine Hosfender or whatever, she commented on Kurt Jaimungal's thing of like, yeah, is superluminal information, and I mean, she's a physicist, she's like, she makes YouTubes, she's like a turbo YouTube physicist. I think it's something she even thinks about herself. So I don't know if it's necessarily like, is there usable bits out of this system, or is it instantaneous collapse in some way that still doesn't violate what we think of as like information causality or something like that?
That's a great question, and I'm a huge fan of Sabina and Kurt. They're both, I love their videos. They do a really great job. So the no signaling theorem says that despite all these strange, apparently non-local correlations in quantum mechanics, you can't use this effect to transmit information faster than the speed of light. I have an analogy for this, and it's not perfect because no analogy is perfect, but just to show you an example of something where you can have something very strange and non-local that's also not a faster than light communication system. Imagine this. So imagine we have a pair of dice, and maybe I have one and you have the other, and we're far away. Now let's say these are magical dice in the following sense. Whatever one you roll the dice, and whatever, okay, we both roll the dice at the same time. Whatever one dice comes up as, maybe say a 3, the other die is also going to come up as a 3. Let's say that this is the magical property of this pair of dice. They are completely statistically interrelated. So if I roll a 2, I know that you've also rolled a 2 in that instant. So that would be an example of something that is very weird and non-local. But if you then take that system, which is kind of, you can describe it you don't need quantum physics. You can just, take it on faith that these dice have this magical property and think about, can I use this as a communication system? Well, no, because neither of us can choose the number that we roll. And so, but we do know, like if I roll a 2, I know, okay, well, you've just rolled a 2. But what can we do with that? There's no, how do I send a message, right? So, and that kind of, even though it's just an analogy, that does kind of convey the essence of the no signaling theorem. Oh, interestingly, just, I know I'm kind of rambling, but on this topic, there is something called quantum pseudo-telepathy, which sounds like a woo-woo thing, but it's actually real.
I'm there, man.
There are some games, like some mathematical strategy games involving 2 players, where if they had a link of entangled particles, so one person's over here, one person's over there, and you have entangled particles between them, and you had these non-local correlations, even though they couldn't use those correlations to communicate, to transmit information from one person to another, they could, with their shared knowledge of those measurements and inferences about then what the other person is measuring, there are some games in which there is a better strategy using that quantum entanglement link. So it's not communication, and it can't be leveraged to build a FTL communication system, but it's just an interesting mathematical fact that there are some games you can play where having a quantum entanglement link actually can help you out. It's fun to think about.
Interesting. I mean, I think of this silly example of like, well, first, I mean, for this entanglement thing, you can't separate the particles from each other faster than the speed of light. So there's still that relationship is still established and it still obeys this causality in that sense. But like we give like submarine commanders like sealed orders, right? And like, if in some situation where it's like you have like 2 different submarines, one order book is going to be this, one other order book is going to be that. You don't know which one has it, but they could figure it out. It's to their advantage when they open the books. There's some kind of tactics they can play because they know what the other person has, I guess, or something like that.
Exactly. And there's a direct analogy to that in the field of quantum cryptography, which is this idea of a one-time pad. So if you have a message and you write it in terms of bits, zeros and ones, any information can be put in zeros and ones. Now imagine that you have something called a pad, which is like, think of it as something that's the same length as the message, or maybe longer, can have extra bits, that's fine. But you imagine like stamping those bits together so that 0 plus 0 is 0, 1 plus 0 is 1, 1 plus 1 is 0 mod 2. So if you and someone else have the same pad, the same list of apparently random zeros and ones, then you can take a message, stamp that onto it, send the encrypted message, and then the other person knows, oh, they've stamped this particular pad onto it, and so then they can recover the original message. That is actually an unbreakable method of encryption, provided that no one else other than you and the other person knows what pad you're using. You can use quantum entanglement to generate these spontaneously. If you have, for example, a pair of spin 1/2 particles in the singlet state, and 2 measurement detectors along the same axis, and so if spin up is here as a spin down there, in real time you can generate this one-time pad, and you can use that, and only you and this other person that is on the other detector knows that list of zeros and ones. So you can use that for unbreakable quantum cryptography. It's kind of inconvenient though. It's not a very easy way to encrypt.
And those one-time pads still have to be like physically transported by less than FTL ships or something in my sci-fi novel or whatever.
Yes, but so yeah, that's right. So any particle always has to be less than the speed of light. What's interesting though is that there's no way for a man-in-the-middle attack to come in and try to say, okay, I'm going to read what that particle is going to be measured as. So like, so you have someone that try to come in and like read off of that stream and like tap into your encryption method. Well, that would collapse the wave function. And so then it just, so anyway, it's kind of a tangent, but it's...
this is kind of cool because I think it gets to this concept of local realism. It's like, maybe things aren't real until they're measured, but once they're measured, they are determined. And in that sense, like this is kind of, I guess, a concept here.
Yeah, and that's there's a lot to say about that.
Well, that gets into this sort of philosophical interpretations of the thing. But let's go back to this, because I think where we landed was, yes, you can have this kind of long distance interaction of instantaneous wave function collapse, but it sounds like that doesn't necessarily mean you break this Heisenberg uncertainty principle or commutation relationship between observing a single particle's both position and momentum at the same time. And so is that, you said this, is that like where the logic or the apparent contradiction of the original EPR paper was?
Yeah, so the apparent contradiction comes from, or I should say, it rests on the assumption that if particle 2 could have been put into a position or a momentum eigenstate, then particle 2 had a real position and real momentum, like associated with it in physical reality. So you can imagine then, from that point of view, quantum mechanics is kind of a loose description. It doesn't factor everything, and it doesn't take everything into account. And so, yeah, but you're right. I mean, this idea that that position and momentum of particle 2 are simultaneously real, it's like, what do you mean by real? Does real mean that it's something you could measure without interacting with the system in any way? If so, then they're both real. Does real mean that they both have to be simultaneously real at the same time? Well, yeah. So I mean, yeah, and that is one of the things when you contend with the implications of Bell's theorem. You have to give up locality or realism. There's a fancy word for it. I'm forgetting it. Outcome. Definiteness or something. Anyway, you have to give up either locality, so you have to assume non-local wave function collapse, which is really problematic, or you have to assume that in some sense reality isn't even real until it's measured, which is, I think, even worse. Or the third option, the third option is to give up the concept of measurement independence and become a superdeterminist, but I'm not a huge fan of that option.
Do you want to, because we mentioned this once before, what is this measurement independence and superdeterminist kind of?
Well, yeah, I should mention it because I know people always like to bring this up. Okay, so, well, first let me try to make the case for why people might put forward an idea like superdeterminism. Like, let me try to steelman the argument. So there's no good explanation for Bell correlations. There's just no like accounting for the mathematical and experimental reality of these Bell correlations that isn't deeply unsettling. And the way I prefer to think about it, which is not a strongly held belief at all, just something that helps me remember.
Bell correlations meaning you can't have both local realism or...
So yeah, thank you for jumping in there, because I realized, yeah, I should define what a Bell correlation is. It's the idea that if you have two entangled particles and you separate them out, and then you measure something about them, and here I'm just speaking generically, but you measure something about the two particles, there's going to be something equivalent to a non-local wave function collapse that is needed in order to explain the correlation between the two particles.
Okay, so that's just the mathematical, like Bell's calculation of determining that is the case. Now you were saying, how does that lead into superdeterminism, or why is superdeterminism like an uncomfortable or most lame possible interpretation?
Yeah, well, and I would say the best case for superdeterminism is just that you'd have to believe that all other possibilities are even more dreadful than superdeterminism. So that's why I was bringing up that my preferred way of looking at it, and this is just so it makes it easy for me to remember the math, is that you just have a non-local wave function collapse, and then you don't think too hard about relativity. But there's a flaw in the way I like to think about it, or not just me, but anyone who wants to take that point of view of non-local wave function collapse, is that we know from relativity that there's no such thing as an objective definition of simultaneity. So if you have an experiment where there's a detector A and detector B, and you're measuring the two particles, and you're measuring them at like the same moment in time, but then some relativistic observer comes flying by at super high speed, what happens in special relativity is imagine you have like spatial dimension versus time. If you're standing still, you have detectors A and B. In time, they just go straight up, like the world lines are like vertical in like the xt plane. And then you see a relativistic observer coming by at a slope in the plane, because as time goes on, they're moving along x. But from relativity, if you then want to shift into that observer's point of view, where they're just stationary and you have the detectors in the lab flying by the other way, the problem is, and the difference between Galilean relativity and special relativity, is that everyone has to always agree on the velocity of light, or the speed of light in a vacuum. And so when you think about, imagine you have the world lines of detectors A and B, but then also imagine some light cones of photons going in different directions, and those are at 45 degrees. Well, okay, so here's the lab frame, here's the frame of the observer. You tilt into the relativistic observer's point of view, the lab frame seems to be going the other way, but the light cone has to remain at 45 degrees. And the only way that can happen is if in the space-time diagram, when you boost from one reference frame to another, all of the points in space-time have to move along these hyperbola of constant space-time interval. And what that's going to do is that's going to tilt the now slice between the lab frame and the relativistic moving person's frame. And so anyway, to bring this all together, the person who's moving by quickly relative to the experiment is going to say, that wasn't an instantaneous wave function collapse. It collapsed at A before it collapsed at B. And so that's a problem. That's actually a real problem. And also, someone coming the other way is going to say, no, actually, it collapsed at B before it collapsed at A. So the concept of instantaneous wave function collapse is inherently fraught, and it's paradoxical. If you take special relativity as absolutely foundational, then non-local wave function collapse is not allowed. Now, I happen to believe that special relativity might be effective or emergent. There's no experimental data to indicate that. But it's at least, it's something I can live with. Is that
so the case? Is that reframing? So if I have two things that, two events that to a stationary observer appear to have a pure space-like separation, right? There's no apparent time-like separation, so they look instantaneous. To some relativistic observer, I end up, the transformation between the relativistic observer frame and the stationary frame is the space and time components become a bit mixed. And so now I see these two events as having some space-like separation and some time-like separation. So they no longer look instantaneous.
Yeah, that's definitely the right idea. But just as far as like space-like and time-like, and I'm sorry if maybe this is a pedantic point, but technically speaking, in relativity, space-like is just anything that is in the outside the light cone.
Right.
But your point is right. So that pedantic correction aside, your point is absolutely right.
So space-like and time-like separation, that's like the magnitude of the 4 vector if it's positive or negative. And so within the light cone, we always have space-like separations. And so, but this is, I was meaning like, if you look at the components of the separation, in this frame, the components are purely spatial. In the relativistic frame, the space-time distance between these two things has some time, has some space components.
Well, exactly. Yeah. So if you define like, everyone, we have this intuitive notion of like a now slice. Like if you, like in this moment, imagine the whole universe. If you define a now slice as the hypersurface in space-time, so you have 4-dimensional space-time, you take a 3-dimensional hypersurface of constant time in your reference frame, and then a moving observer does the same in their reference frame, the events contained in those two now slices are going to be different. So moving observers don't have the same now. There's actually there's a shift.
Okay. So is this kind of where we have come to now? Is that as far as the kind of EPR paper went?
Yeah, I think that just about sums up the EPR paper.
So it's like we have these two entangled particles, they can be separated. It appears that now they have this instantaneous property determination relationship between each other. And their premise was, you can't have this because, Einstein was a little biased towards GR, I guess. And so they reached the conclusion, this is a paradox, therefore cannot exist, therefore QM, quantum mechanics, is incomplete. Is that kind of basically like where they landed?
That's exactly their argument. They saw that this appeared to be a paradox. Rather than accepting that apparent paradox and figuring out what's going on there, they just said it's a paradox and therefore quantum mechanics is incomplete. And at the end of the EPR paper, they say a few words alluding to the idea of bringing in hidden variables in order to make the theory complete. And then hopefully then that would have cleared up the apparent paradox.
Right. And that was in 1932 or 30 something.
35. Yep.
35. Okay. And then enter stage left, John Bell, right? Like 30 years or 28 years later or something.
Yeah. So in 1964, Bell, 29 years later, Bell writes a paper. It's called On the Einstein-Podolsky-Rosen Paradox.
Mm-hmm.
And he basically shows, can we switch to the Bell's theorem slides?
Yes.
I also got to blow my nose again real quick.
Bell's theorem, a glitch in reality. Nice. Well, I'm sure we can all exploit this to get more Claude code credits or something. I choose to observe a universe where I'm not at my token usage. Therefore, unfortunately, it's not how it works. Okay, sorry. Okay, so now we get to Bell's theorem, who comes in 29 years later, and how does he, I guess, approach this? Because I think that was like the next significant step in kind of determining like what can be true in this context of local realism versus superluminal wave function collapse and so forth.
Mm-hmm. So where the EPR paper left off, they suggested that we need to bring in additional hidden variables. And hidden variable just means something that quantum mechanics doesn't currently take into account. It's hidden in the sense that it's not at the moment part of our description of reality. And it could also be hidden in the experimental sense that it's not accessible in experiments, or maybe you would need like a higher energy scale or something to that effect. What Bell shows in his paper, and by the way, just as we're talking about, if you assume quantum mechanics is incomplete, then you can sidestep the whole apparent paradox of if it is complete, then it seems like there's a paradox, therefore it's incomplete. What Bell is saying is
saying it's incomplete, is that just saying there's more than just the Schrodinger equation?
Technically, yes, but it's more like the idea that quantum mechanics is incomplete is that there exist elements of reality that are not described in quantum mechanics, and not just in like an emergent sense of like, like the results of a sports game or something, but I mean like at the micro level. In quantum mechanics, we have, position, momentum, things like that. Maybe there's something missing. Something like spin is a good example. The spin of a particle is kind of a subtle thing, and you can imagine, a model of physics that didn't account for spin, and then someday someone, the Stern-Gerlach experiment comes along, and it's like, whoa, what's this? And so you have to add spin. And then Dirac comes along and shows how that's necessary from uniting relativity and quantum mechanics. So maybe there's something else like that, some attribute that particles have that is just not taken into account in quantum mechanics.
Okay.
So what Bell basically says in his paper is whether or not quantum mechanics is complete or not. I mean, imagine you can bring in local hidden variables. Bell says you can bring in whatever kind of local hidden variables you could possibly imagine. And he uses this symbol lambda to represent that. So actually in the equation shown on this slide, you can see in the integral we have a as a function of a and lambda, b as a function of b and lambda, rho of lambda, d lambda. What that lambda is a symbolic representation of any kind of hidden variable you can possibly imagine. So you can imagine it as like, maybe it's like a direction-like vector quantity, maybe it's some kind of tensor thing, maybe it's a function or a set of functions. And Bell says, okay, so suppose you upgrade quantum mechanics with this additional hidden variable. Well, then it's still not the case that you can get out of that apparent paradox about non-local wave function collapse, or something mathematically isomorphic to non-local wave function collapse. In other words, there are still quantum mechanical correlations that have no explanation within the context of local realism, even allowing for any imaginable hidden variable. Does that make sense?
Yeah, so it's kind of arbitrary. Any hidden variable theory you can imagine. Yes.
Exactly. Yeah, because his argument in this paper is so generic. Actually, let me see. Maybe I'll go a couple of slides here. I have a lot of slides for this one. I want to go to equation 2. Oh, I don't know. Yeah, there it is. Okay, so just without getting lost in the technical weeds here, I just want to zoom in on one particular technical point as it relates to Bell's theorem, which is that if you look at equation 2, you have a correlation. Well, maybe I should, let me take a minute just to describe what Bell's imagining here.
Yeah,
but then I
yeah,
want to return
exactly,
to equation
totally.
2.
Yeah, yeah.
So, okay, so in the EPR paper, they imagine an entangled two-particle state where the momenta of the particles are anti-correlated. So if one has momentum p, the other's momentum negative p, and the positions are perfectly correlated by some offset. In Bell's paper, he also has an entangled two-particle state, but rather than correlated momentum and position, he imagines spin correlations. And this is actually a thought experiment put forward by Bohm and Aharonov. That's reference 6 of Bell's paper, if people want to read about that. So this is a more accessible, more imaginable example of a two-particle state where we can think about non-local wave function collapse and spooky action at a distance and all that. So the basic idea is pretty straightforward. Basically, you create a pair of particles in the singlet spin state. What the singlet state is, it's often described as the particles having equal and opposite spin, but that's actually not quite right, because that could be like a product state. Where imagine equal and opposite spin. That could be particles polarized along this direction, spin up, and the other one's polarized the opposite way. The singlet state is actually much more surreal, and it seems like something that shouldn't be able to exist, but it does. And that is, neither of the particles has a preferred spin axis before it's measured. And yet, you're guaranteed to have an anti-correlation in spin if you measure both along the same axis. That on its own, never mind all this math and arguments and sophisticated quantum physics, just that concept on its own is enough to, you think about it and you're like, that can't be. How can it be? Neither particle has a preferred spin direction before it's measured, but if you separate them out and measure them real quick so that the measurements happen in different light cones, you're guaranteed to find this anti-correlation if you measure along the same axis. That seems impossible, because how do the two particles know which way the other one collapsed?
But is that, I mean, is that, why is that so much weirder than just having one be spin up or one be spin down, I guess?
Great question. That is the question. Yeah.
Okay.
And that's the thing that is, seriously, that is the most important question you could have asked about Bell's theorem, because that gets right to the heart of Bell's theorem. Okay. So when I was first learning about Bell's theorem, I think a while ago, I was like watching a documentary and they were explaining like, particles spin up and a particles, the other one spin down, and like you measured one over here and it was spin up, and then the other one over here was spin down, and it's like, whoa. And I remember just being totally unimpressed, because
right.
Like, well, yeah, one spin up, the other spin down. Who cares? What's the big deal?
Yeah.
And it's sort of like if you have a pair of gloves and you put the left glove in a box and the right glove, and then you send the boxes and you open one, it's like, oh, this is the left glove. The other one, it's like, oh, this is the right glove.
yeah, totally.
There's no mystery there. There's nothing to get worked up about. So, and so then it seems like Bell's theorem is actually, or this thought experiment is actually not that mysterious. The problem is, there is a difference between the singlet state and a product state consisting of equal and opposite spins. The difference is that if you just had equal and opposite spins, the correlation would be 3 times weaker than what's predicted by quantum mechanics and what's observed in experiment. There's a way to see this. Let me go back real quick to the Stern-Gerlach. Let's see. Okay, so this is the Stern-Gerlach.
These are beautiful slides, by the way. These are beautiful slides. We should go through the whole thing at some point. Yeah.
Yeah, it would take 5 hours, but I'm up for it anytime.
Well, you already made the video, so we should all go watch that after. Okay.
But no, it's I think it's really nice also to just go through them conversationally as well, because when I'm making these videos, I try my best to think about like what are other people going to be thinking and how to explain it. But it's so nice to have someone to talk to as well who can ask, and your questions have been really good, so that's super cool.
You're going to have to come back then. We're going to do more of these.
I'd love to anytime. This is a lot of fun.
Awesome. Okay, so what is the framing of this singlet state? Singlet state meaning like the axis of spin is undetermined or not known, or let's dig into this.
Yeah, so I'd say the two defining aspects of a singlet state is you have these particles. Neither of them has a preferred spin direction before measurement, so there's total rotational symmetry as far as how the particle wants to be measured. But the mysterious thing here is, but there's still anti-correlation if you measure both along the same measurement axis. So let's say if you have detector A and detector B measuring along these axes, the singlet state, if one is spin up, the other one's always going to be spin down. Mm-hmm. But neither has a preferred spin direction before it's measured. So to get a sense for why this is weird, I just wanted to say a few words about the Stern-Gerlach experiment, which has to do with spin 1/2 particles. Mm-hmm. So if you have a chunk of silver, and you're heating it up in an oven so hot that the silver starts to fly out the hole in the oven, and then you collimate that into a beam, and you send that through a non-uniform magnetic field, what's going to happen is there's an unpaired electron in the 5s orbital of the silver atom, and for some reason, and for now, let's just take this as magic. I mean, it's really a mysterious thing. For some reason, either the atom either goes up or goes down. It's not a distribution. It's either one or the other, spin up or spin down. Mm-hmm. It's a quantum effect, and so it's very strange. But and the reason we call them spin 1/2 particles is because if you want to say that the difference between those possibilities is one quantum unit, then by symmetry it's going to be plus 1/2 or minus 1/2. So anyway, the thing to notice is that if you do this and you send some random silver atoms through a Stern-Gerlach detector, you get an up beam and a down beam, and then you block one of the beams and you send the other one through. Now you have a beam of atoms that are polarized spin up. And this diagram, this is just a cartoon. In reality, the beam's alignment has to be, it has to be precisely aligned. But yeah. So, okay, so the thing that is important to know is the probability of having a spin up polarized beam of atoms, the probability of that coming out spin up versus spin down in a second detector that's tilted. So what this diagram shows, and again, it's just a cartoon. In reality, the beams have to be aligned and all that. But the gist of it is that when you tilt the second detector and measure the spin along a different axis, you don't get a distribution of outcomes as far as like a continuous range of possibilities. It's still either spin up or spin down for any given particle. It's quantum, it's one or the other. But the probability of measuring spin up versus spin down goes with the cosine squared of theta over 2, where theta is the tilt angle. So that's what's shown in the chart. If you imagine on the left, we have theta equals 0. And so we have spin up going in is always a spin up coming out. Then on the right, as you go to the right on the plot and you increase the tilt angle, and halfway when the tilt angle is 90 degrees, then it's 50-50. So a spin up coming in could be 50-50 up or down going out. And if you go past 90 degrees, then you're going upside down. And so there's symmetry where before what was spin up is spin down relative to when you go past 90 degrees, everything just flips over. And so, so that gives you a feel for like what it means to measure a particle that's polarized, that has a spin polarized along a certain direction, is you have this cosine squared theta over 2 of measuring probability spin up. Another way this is often described is a cosine of theta expectation value. So if spin up is assigned the number 1 and spin down is -1, then cosine theta, which is somewhere between 1 and -1, is the expectation value you would expect for doing a measurement with the tilt angle of theta. It's all the same.
Question on this. This is, I thought the first magnetic separation would get a pure like spin upstream of particles, but now we can split this again by applying some kind of, but is that just because it's like, because it's if they have truly like a random, is this right? Or am I confusing myself? They have some kind of, it's like, I'm thinking like light polarization, right? Where it's like, you have like a vertical polarization filter. Now the light coming in may be incoherent. So it actually has like a random electric field direction. But what comes out is anything that had like some positive, polarization in that direction I guess I'm trying to get at, like, if we separate it into spin up and spin down, then you have this magnet that's further downstream. It's the fact that it's tilted slightly is what gets the spin down, because they were not purely spin up or something. Like, do you know what I'm asking here?
Every one of your questions today is like the most perfect question. So
Okay,
that's
great.
exactly, so I have a diagram on that. So
Yeah.
let's see here. Where, I guess let me just start with these arrows. So if I understand correctly, what you're asking is, okay, so to the first thing you said about is it because it's random? Yeah, so the evaporated silver atoms are presumably going to be randomly oriented with regards to their spin, no matter how we want to think about how to describe spin, whether we just use the normal description in quantum mechanics, spinor valued wave function, or whether we want to also include additional hidden variables, like in this case, as shown on the slide, like these yellow arrows. This would be an example of a hidden variable. So we can call these lambda vectors, and we can say that there's something about the incoming particles where it carries with it this extra directional piece of information that we're not accounting for in quantum physics, but maybe the detector just is going to flip that up or flip it down in accordance with whether it was pointing a little bit up or a little bit down. Does that match what you were imagining?
Yeah, I'm trying to think of this in like kind of a geometric or visual sense, where it's like, is this spin up is like with regards to some convention where I call anything pointing, say, in this direction is positive up, anything pointing in this direction is negative down, or whatever. And I've separated these into two streams. So in this stream, I have all these guys that are like anywhere between here and here, all these guys anywhere between here and here. And now if I had the same orientation of magnet further downstream, it would no change. But if I change this a little bit, now it's like, well, some of them were positive up in this direction, some of them were positive up in that direction. Is that kind of?
That is exactly the situation described in Bell's paper in equation, where is it here? Equation 8 and 9. Let's see, maybe even 7, 8, and 9. But yeah, that's exactly right. So, and to be clear, that is something like a local hidden variable explanation of what's happening here. In reality, or in accordance with quantum mechanics, what you have is a spinor valued wave function. And then when you measure its spin, you're collapsing it onto a spin eigenstate. And so it's different than what you're describing, but what you're describing, it's so worth talking about, because this is what I think most people imagine when they first learn about the Stern-Gerlach experiment, is they assume there is some directional quantity that's getting flipped up or flipped down, and then so it comes out, and then you started with a uniform spherical distribution for the evaporated silver atoms, and then you end up with uniform distributions over the two hemispheres. And then so now the second beam, you pass through the uniform over the hemisphere, but then there's going to be a tilt angle, and so that's going to sample a tilted slice of that hemisphere, right? So yeah, and so here's why. So that seems like that should be the case, and I wish that were the case. It would make reality a lot more easy to contend with, and wouldn't cause me such existential despair.
So what I've just done to explain this is I've assumed there's a hidden variable. Basically, I've assumed there's this hidden variable of that there's some distribution of spin, and you're selecting each half. But you're saying that's the mistake. That's my assumption, that there's that would be the hidden variable, I guess, whatever it is.
Exactly. And it totally seems like that kind of explanation should work. And I think this is why a lot of people, when they learn about Bell's theorem, they implicitly assume that something like that it works, because it almost does. It's a very as a first pass at the phenomenon, as sort of a first order approximation of what might be happening, it's totally sensible. But the problem comes in when you look at what's really going on in the second magnet. So what happens is, let's say we have this picture of the particles coming in with some random lambda vector, so this directional like vector, and the first magnet is going to filter it into uniform over the top hemisphere and uniform over the bottom hemisphere, and we filter out the bottom hemisphere. So now what's coming in, oh, you know what? This is actually not the right slide. Wait, is this the right one? No, I'm sorry. Okay, there's two different things here, because the question can be, does the magnet actually flip up or down the vector so that as it goes along, now it's been flipped up or flipped down? Or does it just passively filter where this vector is kind of pointing up, and so it goes along? So like this, what's shown here is it flips the vector up, and so that's why on the right side all these vectors are flipped up, and then the second magnet flips them along the tilted angle. But then you could also imagine, let's say instead it passively sorts them. So it says, okay, these ones are a little pointed up, so they go up. Now that's a little weird, because it would be strange for there to be such a passive process that results in two discrete beams. But it's not logically impossible. It's just a little strange.
Thinking about this just made me realize that's the weirdness here. It's like if there was this hemisphere of possible spin directions and that they're passively filtering, you'd think the degree of separation should depend on to what extent is it pointing straight up. Like the straight up ones should be the most separated, and the ones that are just a little bit in that hemisphere should just be a little bit separated. But instead, they're actually all separated by the same amount.
Exactly. That's exactly right. And that's part of what makes this so weird, is that it is either one or the other. And so therefore, you are tempted to think that it's probably more than just a passive filtering. It's probably something like flipping up. There's probably some variable that's being flipped up and down in accordance with the discreteness of the two beams. But okay, so suppose that's the case, and an atom goes through, and when it goes up, that means its vector has been flipped up. Well, but then if we just apply a consistent, the rules are consistent throughout the universe, then as that upwards vector goes through, and it goes through a tilted detector, suppose the tilt angle is between 0 and 89 degrees. You're going to get a spin up every time, because the upwards pointing vector, as it goes through, and the other vector is tilted, some 30 degrees, 40 degrees. Well, that's still, the up is pointing mostly along the direction of the tilted detector. So that wouldn't work. See, because this model predicts that in the second detector, we would only have spin ups. But in reality, we have a cosine squared theta over 2 probability of spin up, and then a sine squared theta over 2 probability of spin down. So even at a relatively small tilt angle, you do start to see the separation into two distinct beams. And so this idea...
That's that's how we know it's not doing this spin alignment thing.
Exactly.
So it's not doing the spin alignment, because you'd always just measure downstream. It would always just realign with that spin downstream. Yeah, exactly. So this shows that... if we want to think in terms of these hidden variables, the thing where it just flips up or flips down, it actually doesn't match this is known as a two-stage Stern-Gerlach experiment. But what seems to match, and it doesn't quite, but seems to, is if instead you did have this more passive filtering process, where if the vector points a little bit up, it goes up. If it points a little bit down, it goes down. But the vector itself doesn't change. So this is weird. This is like, at this point, you have to ask, well, how can, it doesn't sound right, but it's not illogical. And so then you ask the question of, what is the statistical outcome of a model like this, where going into the second detector, you have a uniform distribution over the hemisphere, and then you have a detector that's tilted, but the rules of the detector is that if the vector is pointing somewhere along its hemisphere, then it's spin up, or if not, then it's spin down. And the probability calculation there is just the intersection of those two hemispheres, like the wedge angle. And so that gives you a probability that's linear in theta. So instead of cosine squared theta over 2 probability of spin up, it's going to be 1 minus theta over pi. And so that's a slight difference. And I think I have a chart of that here. Yeah, it's kind of small, but you see in the up middle part of the screen. Yes.
This hidden variable model predicts a linear trend. Or I guess I'm backwards. It's this way. But quantum mechanics, it's a cosine squared probability of spin up.
Well, in my simplistic reasoning, you could still get a cosine angle if there was some interaction between the magnetic field and the spin axis, which you'd expect, because I think spin, like it is like this, what is it, like I'm so rusty on this, it's been so long since I took this undergrad quantum mechanics course, but like one way to think about spin is like the direction of movement or direction of rotation of this electron, and that produces like this magnetic dipole moment. And so, the strength of interaction for that should be like a dot product. And so that gives you a cosine thing. Am I way off the mark here?
No, you're actually, you're right on, as always.
Okay. Okay.
So I don't. While you're asking that question, I went ahead to this slide that addresses that exact question. So you're like right on, man.
Okay.
So yeah, because when you see that this thing about hidden variables gives you this linear trend, and in quantum mechanics you see that there's this, it's actually more of a cosine squared. You can just say, all right, then there's some kind of interaction happening between the particle and the magnet such that it skews the line into the cosine. If that makes sense, right? And so the
yeah.
yeah.
This is like, just very simply, like projecting two vectors on top of each other. Like how much do these vectors overlap? In the vector sense, it's like magnitude A times magnitude B times the cosine of the angle between them. You know.
So that's right. So yeah, if you have a particle that's polarized along the vector p, and you measure it along the axis a, then in quantum mechanics, the expectation value of +1 being spin up, -1 being spin down, the expectation value is the dot product of the unit vectors between the polarization axis and the measurement axis. So it is exactly cosine of theta. But that's not what we would expect from this picture of each particle carrying with it a hidden variable vector that gets passively filtered into these ups and downs. We'd expect a linear trend. So we'd have to posit the existence, if we really want to stick with this hidden variable model and make it work, we have to posit the existence of some kind of interaction that is going to rotate the effective measurement axis such that the line warps into a cosine. And now there's no longer a disagreement between our model and quantum mechanics. There's a couple of problems with that, however. One of them is now our model is starting to actually get really contrived because how can it be that you have this situation where a particle comes in and it can go one way or the other way, and it's such a binary thing, and yet it's such a passive filtering thing, and yet still there's this interaction happening that just so happens to make the statistics work. It's hard to believe, but it could be right. It's not logically incoherent if we're only considering one particle. And in fact, in part 3 of Bell's paper, he describes doing exactly this thought experiment. In part 3, equations 4 through 7, he describes exactly this process of inferring some kind of interaction that changes the effective measurement axis of the magnet. And for one particle, that's okay. The problem becomes when you have two entangled particles, and now you're measuring them on two different magnets. And if you want to do the same kind of move where we warp the line into the cosine, now all of a sudden, the measurement axis at one detector has to know what the measurement axis at the other detector is, because the tilt angle depends on both of those. So I'm kind of skipping, I skipped ahead a little bit there. So if you have an entangled state of two, in the singlet state, equal and opposite spin, no preferred spin direction before measurement, if you measure them both along the same axis, you're guaranteed to get anti-correlation. If you measure one along this axis and another one on a tilted axis, one way to think about this is imagine the one on this axis gets measured ever so slightly before, a billionth of a second before, then you can infer that the other one, you can think of it as like, okay, now this is polarized spin down along this axis, but now it's getting measured along this axis. So the statistics depend on the tilt angle between the two detectors. But if you want to do the kind of logical move that turns the line from the hidden variable model into the cosine of quantum mechanics, that depends, that's a function of the tilt angle, because the effective measurement axis has to be a function of theta such that the line and the cosine become the same curve. But the problem is, if the two measurement detectors, the two measurements happen in different light cones, there's no way for one detector to know the orientation of the other or vice versa, assuming local causality. And so you actually are not able to do that mathematical move where you convert the line into the cosine, because you can't assume knowledge about what the tilt angle is between the two detectors that are space-like separated.
That's Einstein's assumption, that you can't.
Well, so this is actually Bell, trying to find where in his paper he brings it up. At the end of part 3, I think, at the end of part 3, he talks about this, and he basically says that because if you want to assume local causality, then there's no way for the detector axes to know about each other.
Right.
And so therefore there's no way to know what that tilt angle theta is at either of the detectors. And but yeah, the assumption of local causality is definitely a part of that. If you want to, if we say, well, never mind local causality, then let's allow for non-locality, then you could come up with a model where the tilt angle theta does factor in, and you can warp the local the hidden variable model's line into a cosine, but then your model has to include the theta angle, which depends on separate space-like separated.
Yeah.
So Bell doesn't rule out. Or sorry, I know I've been rambling.
No, it's good. It's good. Then I'll ask some questions. Yeah.
Great. Okay, so just to clarify, Bell doesn't actually rule out non-local hidden variables. So his claim is not that quantum mechanics is complete and that it's not possible to have hidden variables. His claim is that local hidden variables don't explain the correlations, and so there's no way to fix the apparent paradox with local hidden variables. But of course, I mean, you can always imagine maybe there's, quantum mechanics might not be complete, but those hidden variables just don't factor into the correlations that are observed in these kinds of experiments.
And so, okay, so you're saying he doesn't rule out the ability for superluminal hidden variables or something like that.
Yeah, that's a good way to put it. I mean, it depends. If by superluminal you mean no signaling, then that's a good way to put it. But yeah, okay. So yeah, because really there's no way to rule out the idea that there might be some non-local hidden variables in reality. We just don't know everything there is to know about reality, so that's a hard thing to rule out.
Yeah. Okay, but I think we were getting to this crux of this Stern-Gerlach experiment where it's sort of like, we know that it can't just be this. So we know that it's not the detector that's changing this thing's state, further downstream. And we also know that it's not just this random orientation of an arrow in some kind of sphere that we're sorting by as we go down. And so what is the conclusion we reach?
Yeah, so the conclusion, well, let me go back to equation 2. Okay, equations 2 and 3, this is the thing. So, well, first equation 3, actually first let me just describe the diagram here. So the diagram shows we have an entangled pair of spin 1/2 particles in the singlet state, where neither has a preferred spin direction, both are guaranteed to be anti-correlated if measured along the same axis. Then we can imagine detectors A and B, so we send the particles apart in space while they remain in an entangled state, in the singlet state. And then if you measure them along the axes A and B, so imagine these are Stern-Gerlach magnets tilted along A and B, then quantum mechanics predicts, and experiments show, that the expectation value of the correlation between these measurements is going to be negative cosine of theta. And that comes exactly from thinking about if you have a particle going through a Stern-Gerlach magnet and thinking about if it's polarized one way and then you measure it at a tilt angle, what is the expectation value? It's the same logic as if you imagine the first particle getting to detector A ever so slightly before, then now the second particle you can think of as polarized opposite to that, and then it's passing through a tilted detector with axis B. Well, then the anti-correlation is going to bring in a minus sign, and the tilt angle is going to bring in a factor of cosine theta for the expectation value of that result of the correlation. What equation 2 is a description of the correlation given some detector settings A and B as a function of that includes hidden variables. So what the integral is you're integrating over the whole space of possible hidden variables that you can imagine. This is like the most generic thing ever, because the hidden variables can be whatever you want them to be, a vector, tensor, function, set of functions, whatever you want it to be. And the idea is consider all possible hidden variable configurations, integrate over all of those, weight that by the probability distribution, so how likely a configuration is to be as far as the hidden variables. And then for each of those possibilities, weighted by its probability of it being that particular configuration, you just multiply the measurement outcomes at detectors A and B. So these take on the values of +1 if it's spin up. So if A is +1, then particle 1 is measured spin up at detector A. If B is +1, it was measured spin up at detector B. And so you basically, in equation 2, you're taking the product of these outcomes at detectors A and B and integrating it over the whole space of possible hidden variables. And what Bell shows is that equation 2 cannot equal equation 3. That is to say, no local hidden variable model can explain the correlations that are predicted by quantum mechanics and that are observed in experiment.
Okay.
I know, sorry, I know it's kind of a lot, but
no, it's a lot. It's a lot. How does he show that there's no? I mean, is this like a math proof type thing? Like, how does he show that there's no way to make there's I guess what you're saying is there's no way for this hidden variables thing to get what we observe, which is this like cosine squared relationship between tilt angle of the second magnet and how much spin up, spin down we get.
Yeah. So yeah, it is a math proof. It's actually, technically it's two. He proves in two different ways that equation 2 is not going to be equal to equation 3, or even approximately equal to. So the first way he shows is that, so equation 2, you have this correlation function, P as a function of the measurement axes A and B. That is going to be, that's going to take on a value between -1 and 1. So for example, if A and B are perfectly aligned and you have the singlet state, so if this is spin up, this is spin down, that's going to give you a perfect -1 correlation, because you have A measures 1, B measures -1, or vice versa, B measures 1, A measures -1. In either case, the product of A and B is going to be -1. And so when you integrate over the space of all possible hidden variable configurations, you get a correlation of -1. On the other hand, if A and B are anti-parallel, then you have a correlation of 1, because the singlet state, if this one spin up, that one spin down. What Bell shows, the first thing, and it's kind of a subtle point, is that if you look at the minimum value of the correlation function, which takes on a value of -1 for when the vector A equals the vector B, in any local hidden variable model, you think about the correlation as a function of those vectors, it's not going to be stationary. There's going to be a slope there. Or even like, the absolute value function, maybe it slopes both ways, but it's going to be a point. It's not going to be a zero slope. Whereas in quantum mechanics, negative cosine of theta, that's a zero slope at the minimum. So, and that is a generic difference between any local hidden variable model and the correlations of quantum mechanics, is that in quantum mechanics, at the minimum value, there's zero slope in the correlation function, but any local hidden variable model is going to have a non-zero slope at its minimum value. So that's number one. That's the first thing that Bell proves to show that local hidden variables don't match the predictions of quantum mechanics. And of the two parts of his proof that he puts forward in part 4 of the paper, that's the easier one to follow, but it's also kind of the weaker one, because it's like, who cares about a point at the minimum? What you really want to show is that a local hidden variable model can't approximate to arbitrary precision the correlations of quantum mechanics. And so that's the second part of Bell's argument in part 4. It's pretty sophisticated. I go into it in my video, but it's a lot of math, and it's just
we can defer it for now. I think I'm sticking to my kind of smooth brain mental model here, which is like thinking of this random direction in the hemisphere thing. That is a hidden variable. That is a hidden variable, essentially. That is extra information about the system I'm using to describe the system, but that extra information doesn't actually match what we observe with this experiment. Again, in my smooth brain interpretation, it's because it's like, well, this continuous alignment would not result in this discrete outcome, I guess. And like you said, it would also have this linear relationship. It would not have a zero slope at the minimum. It would be like, well, any little bit in the up hemisphere would get you more of that measurement. So I think I'm going to stick with this simplistic kind of thing, but it's very like geometrically intuitive, I guess.
Exactly. Well, yeah. And so the idea that that's exactly the right intuition to have, is that local hidden variable models tend to give you correlations that are linear in the tilt angle theta. The reason being, if you imagine like just the overlap of two hemispheres, it's like a wedge, and then the size of that goes linearly with the wedge angle. Or really, it's in 3 dimensions. If you imagine like an orange slice, like you're eating an orange, and you have a slice or 2 slices, the one that's twice the volume has twice the angle. So it's the same kind of thing.
Okay. Yeah. Okay. I'm following.
Okay. So now there's one, we started, we talked about this, I think, I don't know, maybe it was half an hour ago or something, but this is the thing. about, the left glove and the right glove. It's like, okay, this one spin up, this one spin down. What's the big deal? So for those who are reading Bell's paper, you want to look at equation 11 and the surrounding text. I won't go into that for now, but that's where to look in the paper. If you imagine that instead of being in the singlet state, the particles are in what's known as a isotropic mixture of product states. Sounds like a technical word, but all that means is any given pair has some spin axis, call it n. So you make a pair of particles, and this one's polarized up along n, and the other one's polarized down along n. That's known as a product state. It's a separable state where you can say, okay, this one's polarized that way. That one, its spin is going to be polarized equal and opposite. And then isotropic mixture just means you're doing an experiment where there's some symmetry involved, such that you'd expect these directions, this spin axis n, to come out pretty randomly distributed over the sphere as you're making multiple particle pairs. And this is what people implicitly imagine when they first learn about Bell's thought experiment. They secretly, I think, at least this is when I first read this, I thought, wait, isn't this how it is? Is that each pair has equal and opposite spins. The reason that's different from the singlet state, and the reason this is actually more than just left glove, right glove, is that on average, let me use this to indicate. So suppose this is the spin axis n that the particles have spins equal and opposite relative to. Well, if n is straight up and we're measuring vertically on our two measurement axes, then in that case, we'll get a perfect anti-correlation, because one of them is going to be spin up, the other one's going to be spin down. But if, let's say, suppose for the sake of argument, n is straight up, or no, actually rather, suppose n is horizontal, and now we're measuring along these vertical measurement axes. Well, now if it's really a product state where it's separable and there's no entanglement, in any case, the particle has 50-50 chance of going up or being spin down. If we're measuring along these directions and the spin axis is along this direction, we know from the Stern-Gerlach experiment that can go either way. And so we don't have a correlation between the particles in that case. What happens when you consider the isotropic mixture, meaning you sample uniformly the whole sphere in 3 dimensions, you're creating many possible pairs, you're supposing each one has some spin axis, and then that's sampled uniformly over the sphere, you find an expectation value, not of the cosine theta that's observed in experiments, but a cosine theta over 3, where the 3 comes from the fact that we have 3 dimensions of space. And on average, there's not going to be an alignment between the measurement axes and the spin axis of the product state of equal and opposite spin. Does that make sense? It's a subtle thing.
I think so, yes. Basically, the axis we choose is one-dimensional, and this, you're saying, the mental model is that it has a random distribution over all 3 axes. So you kind of get this, yeah.
Well, so what I'm imagining there is
over all 3 directions, yeah.
Yeah. So the question, what it really comes down to is, in either case, we're dealing with something that has a kind of spherical symmetry. In the case of the singlet state, if we believe the quantum physics orthodoxy, we would say there genuinely is no preferred spin direction of either particle until they're measured. Mm-hmm. But if you want to take a more classical view where the particles have equal and opposite spin, and it's just that the axis is chosen randomly when the particle pair is created, it's in a way it's similar, but in a very important way it's different, because that spherical randomness is already selected for at the time the particles were created. It's not something that is determined at the time of measure, and that's the essential difference.
Yes.
And so the fact is, and this is, when you see this, it ruins your whole life, because you realize there's a glitch in reality. And it's like, I'm half joking. No, the other day on X, I jokingly tweeted that, can someone find me a therapist that has studied Bell's theorem and can help me through the implications? And it really is amazing. But anyway, so the point is that there is a way to tell apart those 2 situations, the singlet state versus the isotropic mixture of product states. Not only is there a way to tell them apart, but the signal is huge. It's a factor of 3 difference in correlation strength. And the way to imagine that is just imagine the first particle getting to detector A ever so slightly before the second particle gets to detector B. Well, now the second particle, if you can think of as polarized opposite to the measurement axis A. And if you see that, that's the kind of alignment that you don't have in the case of an isotropic mixture of product states. And that's why the correlation is stronger when you're dealing with a singlet state. But in order to explain that, you have to imagine something like one particle being measured, its wave function collapsing, the other particle therefore behaving itself and being collapsed the other way, and then measuring that particle. And so that's the picture I go with, just to remember the math, is just imagine a wave function collapsing. But there's serious like existential implications to this whole situation.
Let's get into those next, because I think there's some degree of understanding or intuition here for like how we can kind of rule out different interpretations about this kind of at least visual intuition for what's going on. But then why is it so unsettling for you? Like for you, and I mean you've dug into this in these 5-hour long videos to a degree of like mathematical, I guess, rigor, so as to like satisfy all your curiosities. But you say it's so disquieting. Like what is so uncomfortable about this to you in your experience?
Well, just the fact that it doesn't have an explanation in the context of local realism. I mean, so let me give you an example, and this is another analogy that's not a perfect fit to the situation, but that does capture the weirdness of the situation pretty well. So this analogy would be, imagine, actually it's the same as before. Imagine we have this pair of dice, you have one and I have another one, and we roll them at the same time. And let's say for whatever reason, they always turn up the same number when we both roll them. Well, if that were actually a thing that was real, if we actually had those dice and we were rolling them, it would just change our whole life. We'd be like, wait, this is real? Like, no, something like that should only ever be a hypothetical, paradoxical experiment that can't exist in reality. But these Bell correlations are like that. They're like having a pair of magic dice. Now, the correlation is not as strong as the dice being the same every time. It's a little more subtle than that. But the essential thing is that the correlations have no explanation in the context of local realism. And so there's just no way to make sense of it without abandoning something foundational about your understanding of reality. So that's why I find it so unsettling. I'm like, what's going on here? What's all this about? This doesn't make sense.
Well, now, okay, so but the Bell's theorem conclusion, do we not have a bit of a choice? Like, because we could either accept this local realism, or we could accept this kind of instantaneity of things, or do we have to kind of accept both? I guess. Like, do we have a
no?
And is it like at least one of these things is true, or is it either or like only one of them is true? So
let me just check my notes here, because there's a term that I always forget and I want to get it right. Okay, yeah. So so when you see the weirdness of Bell correlations, there are at least 3 ways to get out of that, or to say, okay, I have an explanation for what's going on here, but it requires abandoning one or more of 3 possible assumptions. And really, this is maybe a bit of a controversial thing to say, but I think it's really 2 assumptions, and then one thing that's such an assumption, it's not even an assumption. It's an axiom. Anyway, but the 3 things are locality, and this is the one I always forget, but counterfactual definiteness, also known as outcome realism, which is kind of just the idea that reality exists. It's hard to say, but it's like reality exists before it's measured. So that like when the particle is on its way to the detector, there is something about that particle that's real, such that when it gets to the detector, it's going to be, there's a measurement that can be made. So basically it's real, loosely speaking, the idea that reality is real. But this one I struggle with, because I have a hard time imagining an ontology that doesn't have outcome realism. So maybe that's just a shortcoming on my part. But anyway, the third thing is measurement independence. And this is the one that I would argue is really not even an assumption so much as just such an assumption that you don't even have to assume it. And that's the idea that the measurement axes A and B are uncorrelated with the hidden variables lambda, or with the particle pair that's being created in this experiment. And so, sorry, go ahead.
That one is a reframing of that, basically saying that like you have these two detector measurement magnets, whatever. Things upstream don't really know what's downstream before they get there.
That's a good way to put it. I think that gets at part of what's going on, but yeah, it's like, what's a good way to describe it? Well, imagine this. Let's say we have the experiment of the kind that's shown on the screen there, where you have the detectors A and B. Mm-hmm. And let's say we make a random number generator. At A and B, we'll have two random number generators. We'll have one at A and one at B. And these random number generators can be based on any physical process you want. You can have a thermometer, like a digital thermometer, and read the 10th decimal place or whatever pseudo-random or random number you want to generate. You could have, a thought experiment is maybe you have your detector and you're tying ropes to it, and then these ropes are held by a bunch of chimpanzees that are just, going crazy and tilting the detector with just, totally randomly, chaotically. And but at every moment, you're at least recording the orientation of each detector. Well, the idea of measurement independence is just that what's happening at one detector is independent of what's happening at the other detector, and is independent of the particle pair, so that there's not some grand cosmic conspiracy to produce these Bell-like correlations. So it's just the idea that you can have independent systems at detectors A and B. And by the way, so this is not just a comment about determinism. Superdeterminism goes beyond determinism, because let's say if we have a pair of dice, I have one, you have the other, and we roll them, in real life, in reality, there's no correlation between what I roll and what you roll. These things are independent. And yet you can describe that situation in the context of determinism, where the outcome rolled by the dice is completely, you can imagine, okay, if you factor in all the air molecules and all the thermal vibrations and the surface and you can imagine in principle predicting what the outcome will be. But in reality, you still have independent outcomes when you roll these two dice. Mm-hmm. So determinism alone is not enough to violate this assumption of measurement independence. What you need is, and by the way, there's different levels of determinism. That's another topic, different strengths of determinism. What you would need in order to have something other than measurement independence is like the strongest possible determinism, where if you know the state of the universe at some time t, you can, in principle, march forward deterministically in time and figure out what's going to happen throughout all the rest of time. You need that combined with what Bell calls a conspiracy of initial conditions. So, and that's how superdeterminism goes above and beyond ordinary determinism. It says you have very strong determinism, keeping everything, from the dawn of time, whatever was baked into the Big Bang is now unfolding today. And the Big Bang was super specifically configured such that we see these strange non-local Bell correlations. And personally, I don't find that believable at all. Right? It's just, how can that be?
It's also like we live in a clockwork universe, basically. Like it's sort of everything is configured from the beginning, and now it's just unfolding exactly as it has to, or something.
But it's that and more. It's a clockwork universe where there is a conspicuous arrangement of initial conditions, where you would think that's not how it is. It's deeply unnatural. To give you a good analogy, imagine in this thought experiment with a pair of dice, let's say these are magical dice where whatever I roll is the same as what you roll, and we're trying to explain what's going on here. Well, the natural explanation would be something like these dice are linked somehow. They have something, they're somehow entangled, so to speak. What superdeterminism would say about that is more like, oh, there's no problem here because the universe is superdeterministic. It is what it is. These things just happen. And the reason we keep rolling the same number is because that was baked into the initial conditions of the universe. Mm-hmm. But if someone put forward that explanation, you would say, no, come on. That's like Bell said, it's a conspiracy of initial conditions. Like, how can that be? But we do have to admit, if we're being mathematicians about this, we have to admit it's not a logically incoherent explanation. It's just deeply unsatisfying. Also, and sorry, I know I'm kind of rambling, but it is also formally unfalsifiable. Superdeterminism predicts everything. It prohibits nothing. It is completely compatible with the results of any imaginable experiment. And therefore, it's not an idea that can be tested scientifically.
Yeah, it sounds like it would also violate any concept of free will, you know,
Oh, yeah.
part of individuals. Like, so there's no free will. And I think this is how they talk about this in this these papers on local friendliness, where they kind of frame things in a similar way, where it's they were at the same position. And we should talk about that another time, where so you earlier talked about this this relativistic frame translation, meaning someone might disagree on the simultaneity of events or the temporal ordering of events, but they would agree that an event has happened or not, right? Like they would, at the end of the day, there would still be this kind of record of what has happened, just disagreement over the ordering. This extended Wigner's friend thought experiment goes into this, and I don't know if you've done a video on this, but I highly recommend it, where they end up in a similar place with this Bell's inequality, where it's like we have to either relax local realism or the superliminal information or local realism. Things are like real independent of being measured as real, or this objective reality. Like there's an even bigger grand and this is the craziest one, where it's like, no matter, regardless of relativistic frame translations of any kind, people will actually disagree on what has happened and like the list of events. And like, if I apply textbook quantum mechanics to figure out what the initial state was, this person will reach a different conclusion than this person over here, some fraction of the time, whatever, a 12th of the time or something.
Right. Yeah. I mean, yeah. Once you start looking into like, okay, what are all the ways that local realism can be false? Man, it's unsettling. And no one knows. There's no good explanation of how do we make sense of Bell's theorem. There's just a whole a list of alternatives, none of which are good.
What is your personal, I guess, mental model coming away from this? I mean, is there a preferred interpretation in your mind? Like, how do you make sense of things, or are you still looking for a Bell's theorem therapist?
I am still looking for a Bell's theorem therapist. So if anyone out there watching this is a therapist and has studied Bell's theorem, please let me know. I would love to talk to you.
Yeah.
I have a very provisional view of this, that I know my understanding of this is deeply problematic, but to me, it's the least worst option. And so I don't hold this perspective with any kind of emotion or strength or anything, but just so I can remember the math, I like to think about it in terms of non-local wave function collapse. If you allow for that, then you can make sense of these kinds of experiments.
Yeah.
But to be clear, it's deeply problematic. This notion of non-local wave function collapse, it does not mesh well at all with the concept of simultaneity or the lack thereof in special relativity. So, and if someone really wants to take special relativity literally, then I'm wrong. Then non-local collapse is not, it's just a non-starter. And so I think that's why a lot of people are, or not a lot of people, but that's why some people resort to superdeterminism, because they're just not willing to go against special relativity. And it's like, fair enough. I mean, special relativity has been super well tested in a variety of contexts. But then the one little extra level of nuance I would put on that is, it is possible if you wanted to say, okay, imagine you're trying to construct a model of physics where observers that live in that reality observe special relativity up to the kinds of energy scales and length scales that we've observed. You can do it. It is possible to do. It's not, and there's a variety of models out there like this. Like I believe there are various kinds of superfluid vacuum models, which I don't believe in. I think those are very speculative, but I think those do have the property of a kind of emergent Lorentz invariance. And so if I had to guess, if I had to put money on what is the explanation of these Bell correlations, I'm happy to just say, well, I guess we have to give up locality. I guess special relativity is not as absolutely fundamental as we might think, but that's not something I'm confident in at all. It's very strange. There's no good explanation. I'm sorry.
There's no good explanation. Yeah. But I think this is why this is such a cool thought space to live in, because it's kind of like historically, it's like before quantum mechanics came on the scene, there was this view that was like, yeah, we pretty much wrapped it all up. I mean, there's a couple loose ends, and we're gonna figure it out. And there's this like weird thing about like how do you what is it, the ultraviolet catastrophe or something, like you can't predict exactly like how much energy comes off a fluorescent or a hot filament or something, and then Max Planck got involved and led to this kind of Planck's constant, like ansatz, that the energy states are quantized. And then that kind of opened this whole thing. And now it's like, now we're at this similar-ish point where like the standard model of particle physics, really well tested, extremely well verified. We have a pretty good understanding, but there's a few things like what are the interpretations of this in a philosophical sense? There's a couple other kind of lingering things around like, what is it, CPT violation or charge parity time symmetries. There's a couple loose ends there. There's some views of cosmology, like the lambda cold dark matter kind of cosmology maybe under attack from different observations of different supernovas. So it's kind of like this, it's like a similar kind of framing of like, we have a lot of like really solid physics, but there are some gaps in how we can explain things to ourselves and each other that maybe they could be resolved with like a really, there's just a couple extra things and it's actually we're all pretty much there. Or maybe there's like this window to a whole new realm of weirdness that we're gonna have to get into. And it's similar to how, the GR revolution in our thinking of stuff, in that there's the Newtonian universe of like, there's just a single now moment. That was a big upset. Like, what do you mean time is relative? And like, that's weird. And now there's another, but we kind of digested that. And now there's this new frontier of weirdness of like, well, yeah, I think personally, I am not against this sort of interpretation that we may live in a kind of observer-centric reality in some way, where it is the act of observation that is like sampling from the space of possibility that is constructing into definite outcomes, things that otherwise are not definite. I know that's kind of like the it from bit sort of theory, like the John Archibald Wheeler and other guys like that. They were kind of thinking about things in that sense where maybe it is like an information theoretic landscape that we live in, and the act of observation is like, and so that's now, so we don't have this local realism that we like to think of, like things exist independent of just me checking up on them. You know what I mean?
Mm-hmm.
Yeah,
absolutely. And, to your point about, so I forget who said it. It was at the beginning of the 20th century. Someone, it might have been Lord Kelvin, said that, don't study physics. It's basically all done. Right?
Yeah, totally.
Yeah.
Yeah.
And then
there are similar phrases from that time of like everything possible has already been invented, because they were like patenting like AC generators and stuff.
Yeah. Yeah. And then you had Max Planck came along, and we've been dealing with the consequences ever since. What's interesting is that, and this goes to this concept of the unreasonable effectiveness of mathematics and the natural sciences, which is that math and mathematical reasoning is somehow, for some reason, able to show us things about reality that go beyond our senses and that go beyond the world that we evolved to inhabit. And I know nothing about what consciousness is or any of that, but I do know it seems to be that we are the products of natural selection and evolution. And to the extent that our psychology plays a role in that process, we are going to be more or less adapted to survive in a world at the physical scale in which we exist, the time scales in which we exist. We're adapted to navigate in this world with the kinds of forces that you need in order to move around and throw stuff and find truth. But that is such a narrow subspace of the space of all possible things that can be real. And something that's interesting to think about, and even though sometimes it can be a bit nauseating, is how much farther out does reality go than what we are familiar with? And
yes.
And I think the answer is a lot. Like a lot.
Yeah. Well, this is actually a perfect segue, because tomorrow I'm going to have another guest on talking about exactly this. And this is, he's building up on kind of Stephen Wolfram model, the Rulliad, as like a really interesting concept, which is like, it's the space of all possible computational universes, right? And so getting into like, how does your construction as an observer essentially determine like the laws of physics that you experience, right? And certainly in our sense, like we are classical scale entities. We live like at the meter joule second time scale. Like this is not the realm of quantum mechanical systems. And I think for a long time, we've also assumed that biological processes in general are not inherently quantum mechanical, that there's still sort of this like kinetic molecular model is the right mental model to have. I think that's now getting pretty much blown apart by this like realm of quantum biology. So many molecular signaling pathways, molecular interactions and stuff like that. Like there's like quantum mechanical processes are relevant as phenomenon. And, you know, like I frame it as like, however physics works, because biological systems kind of explore this configuration space agnostically, we will evolve to leverage all the laws that may be relevant, regardless of how they work, regardless of our understanding or assumptions of how they work. Now, at the level of our experience, there's a huge degree of abstraction, right? Mm-hmm. Like we don't know how consciousness works or how our brains, like we have some models of synaptic action, although like Hameroff and Penrose are very much, going beyond this. Is like, subcellular structures like the cytoskeleton may be relevant here, and there may be like interesting things. We'll get into that in other sessions, but I think this is cool, man. This is really cool. Thank you so much for coming on and explaining this. I feel like at least we haven't like resolved, I think, and I mean, no one has really, like, what is the correct interpretation of what is physically real? But I think we've at least put like bounds on like, how do we get to this place where we have to accept some degree of weirdness, right? And it's kind of one of these three flavors of like local realism or instantaneity or superdeterminism, which I would agree is kind of seems lame or I would reject it on philosophical principles or just unlikelihood or whatever. So I'm curious, where are you focusing next? What else are you interested in researching? Because you've been producing these videos that I think are extremely high quality, very in-depth explorations, mathematically rigorous. And I suggest everyone that's watching this, hey, there's like 1,200 people watching this right now, cool. To go check out. Yeah. Richard B. Hill, he's awesome. I'm curious, where are you exploring next, and what else is on your mind these days?
Well, I'm currently working on a video on the thermodynamics of black holes. And so that's been like, what I love about being able to do YouTube full time is that I can really dive into each video with like an intensity and a passion. And so that's great. So lately I've really been thinking all about black holes. And that's really been my life these past few weeks, and it's coming along, but man, it's a tough one. So the video is going to be based on the 1973 paper called "The Four Laws of Black Hole Mechanics." It's by Bardeen, Carter, and Stephen Hawking. And in this paper, they use general relativity to explore the properties of a rotating black hole, and they derive a formula for the mass of the black hole. And then they take that formula and they say, hey, this kind of looks like, they draw an analogy to thermodynamics. So you have the four laws of black hole mechanics, which is an allusion to the four laws of thermodynamics. And there's a really interesting crossover between thermodynamics and purely general relativity. So anyway, it's a super fascinating topic. And I hope the video turns out well. It is, I think it's tough. I bit off a bit more than I could chew, perhaps, but I'm in it right now. I'm like, every day I'm like, all right, let me just make a little bit more progress, and
that's
I hope
awesome.
it'll turn out.
Yeah. Well, come back when that's finished, and I mean, we can kind of refer back to that. But that's a topic I've also read up a lot on. It's very interesting. Like it's like the maximum entropy object possible is a black hole. Like that's this Bekenstein bound thing. Like if you approach the limit of like how much entropy can fit into a given volume, like it reaches the entropy of a black hole. And it turns out that the vast majority of entropy in our universe is like locked up in these black holes. Like it's kind of interesting.
Oh, I didn't know that. Wow.
Yeah. I learned that at a party recently. There was a black hole physicist there talking about some interesting things. So
man, you go to cool parties.
San Francisco, man, it's great. Yeah. He was there. It was a Christmas thing. Well, I mean, it was my friend's thing. He did the paper on local friendliness, so he's deep into the frontier of physics research. But this has been awesome, man. Okay, well, everyone, check out Richard's work. It's really fantastic. I think you give like a comprehensive overview of topics that go even beyond like the depth you'd even get in a PhD program. So I think it's very impressive.
Well, thanks, Andrew. This has been a lot of fun, and I'd love to do it again sometime.
All right. That That sounds great. Okay, cool. All right. We'll see you soon.
All right. See you later.
All right. Cool. Well, that was another Hyperstition broadcast, and yeah, we'll keep doing these. They're great. So tomorrow, I mean, that was just the beginning of the weirdness of physical reality. You know, do things exist independent of our observations of them? Can information reach us from outside our future light cone? Sounds like we have to accept one version of that if we want to at least like explain our own experiments, you know, mathematically. But things can get even weirder, actually. And tomorrow's talk is with Sam Pinchal, who he's a very interesting guy. He's built a couple very successful companies in kind of financial space in you know, algorithmic performance improvements for like exchanges and blockchain. And he's recently become an independent researcher looking at this sort of, what is the physical construction of reality through an observer's interaction with this kind of this computational space of what is possible. And he approaches this with an application of category theory. And this is extremely interesting. It has direct connections to Michael Levin's work in this kind of space of Platonic ideals, as well as Stephen Wolfram's work in this kind of computational model of the universe, the thing he calls the Rulliad in his work there. And that is going to be very interesting, because he starts at that, like the very rigorous mathematical treatment of these topics, and then extends it all the way into the realm of, you know, spirituality and meaning of life, and how do we, you know, uncover truth and our experience, like not just like, you know, here's some silver particles passing through a magnet, but here's us as individuals. We are observers. We are measuring reality. We are constructing it with our interactions with things. So that'll be a very interesting topic, and maybe we'll keep Fridays to a kind of philosophical exploration of these things. So yeah, thanks again, once again, for tuning in, and we'll see you tomorrow at 1 p.m. PST.